Greetings, I'm Alexander Lems and I'm here to talk to you about a paper entitled Minimal Perturbation in University Timetabling with Maximum Satisfiability. This is joint work with my supervisor Pedro Monteiro and Inês Lins. First, let's start with a brief outline of the presentation. We will start by motivating you to the topic at hand, then we will discuss different types of disruptions that occur in universities, then we will give a brief description of the international timetabling competition for which the solution discussed in this talk has participated in. Then we'll discuss the solution architecture that has a strong preprocessing background and uses a MaxSAT solver. Then we'll discuss the results, and finally we end the talk with some concluding remarks. So everything starts with a problem, and then we find a solution. However, as time goes by, the problem changes, and we need to reassess the solution. However, the validity of the solution may no longer be valid. And so, the goal of this work is to make this process automatic. So at IST, it's still handmade. Now let's consider a timetable with 4 time slots, 3 rooms and 4 classes. Now imagine that room 2 has to close down due to COVID contamination. So we will need to change the assignment of class 2 and 3. Hypothesis 1 is to change class 2 to room 3 and class 3 to room 1. This has a Hamming distance of 2. The Hamming distance is the distance between the original solution and the new found solution. As only 2 classes change assignments, the Hamming distance is 2. Now let's consider that the timetabling has a soft constraint relating to the precedence or order of the classes. So class 1 has to be taught before class 2, and class 2 has to be taught before class 3, and so on. The original solution has cost 0, as this constraint holds. However, the first hypothesis has cost 1, as this constraint does not hold. However, there's another hypothesis with the same Hamming distance, so only 2 changes, where we change class 2 to room 1 and class 3 to room 3. The Hamming distance is still 2 and the cost is 0, as the precedence constraint holds. So there's a study published in the Journal of Scheduling that analyzes the 5 years of disruption at IST. So we can see that changes in curriculum during this period were rare, and changes in overlap constraints and number of lectures are not that important. The most important disruption is the modifying enrollments that can be explained by the fact that students change their enrollments frequently, as they can choose their own elective courses, and that normally changes year after year. The two other major disruptions are changes in time assignments and room assignments. Please note that this study is before COVID, so these numbers are likely to grow. For example, room assignments will probably increase due to COVID contamination of rooms, as we discussed in the example above. And the room assignments and modifying enrollments probably will increase with the reduction of room capacity due to social distancing rules. So the International Timetabling Competition has 13 instances from 12 universities, 5 continents and 9 countries. You can see the flags up there. The problem is characterized by a set of courses with different configuration of classes, a set of rooms with unavailability periods and travel durations between them, a set of students with a set of courses they must take. Each class is characterized by a set of constraints, a set of possible room and time assignments, a length and a limit capacity for the students that can attend. Please note that all rooms in the domain of a class have enough capacity to seat all students. So the objective here is to assign to each class a time and a room, to section students into classes, and to optimize all soft constraints, including travel restrictions between rooms. A solution presented in this paper finished among the top 5 of the International Timetabling Competition. So, the solution per se. It has a problem instance, a set of disruptions, and the original solution, and we feed it to a MaxSAT solver. However, it's not that simple. We need to preprocess the instance. So we have 2 preprocessing techniques. One is to create sub-instances, and the other is to merge students. So let's dive into the preprocessing techniques. The first one is to create sub-instances. We want to create self-contained sub-instances that can be solved independently. So in order to achieve that, we need 4 things. One is to ensure that the set of courses between 2 sub-instances are disjoint. That goes as the same for rooms and students. The sets must be disjoint between 2 sub-instances. However, this is not enough. We need to ensure that one class two classes from two different instances do not have any constraint between them. So the constraints must relate only to classes of the same instance, and this way we can solve them independently. So the other preprocessing technique is to merge students. We want to create clusters of students as large as possible that have exactly the same curriculum plan. Here we have an example where course 1 has only one class with a limit of 4 students. Course 2 has two classes, 2 and 3. Both classes have a limit of 1 student. In this short example, we could consider these 4 students as independent. However, in larger uh, instances, this wouldn't be practical. So we could consider to merge all students into one big cluster. However, as we can see, S1 and S2 have a different curriculum plan as S3 and S4, as S1 and S2 must attend course 1 and 2, and S3 and S4 only need to attend course 1. So we can split this into clusters. However, this is not enough. The green cluster is fine, S3 and S4 have exactly the same curriculum plan. However, S1 and S2, even though they have exactly the same curriculum plan, this cluster is not enough, as class 2 has a limit of 1 and class 3 has a limit of 1. So a cluster of 2 will not be good for sectioning. We need to split them into a red and blue cluster. So we need 3 clusters to solve this small example. So, the MaxSAT encoding, we have 5 decision variables, all Boolean. 3 of them are relating to time assignments, one for week, day, and hour. Another one is relating to assignment of a class to a specific room. And the last one is relating to the student section portion of the problem that relates the assignment of a cluster of students to a specific class. So, a few examples of constraints. Most of the constraints in this encoding are binary clauses. Here we have an example of 2 classes that cannot be taught in the same time slot. This shows us the advantage of having separate variables for the time assignments, as we don't need to consider weeks or days for a constraint relating to time, to the starting time of a class. So this reduces the number of constraints needed. We also need exactly one constraint. Here we have an example of class C that can only have exactly one room assigned to it. We will need exactly one constraint for all decision variables. Uh, we also have another type of constraint that at most k. Here we have an example of a max day load constraint that ensures that all classes in the day, their duration is smaller than k. Please note this is a small example of the number of constraints in the international timetabling competition. There are 19 different constraints, all explained in the paper. So, the results. We run everything with a time limit of 6000 seconds. More of that is unnecessary as the solution stops improving after that. We use the TT OpenWBO Inc. SAT solver that won the weighted incomplete track of the MaxSAT evaluation of this year. At the time of the submission of this paper, we only solved 20 out of 13 instances. The value increased, fortunately. The quality of these instances are in the same order of magnitude as the best known solutions today. The simulated annealing approach only solves 16 out of 13 instances. This is an approach by Gashi that also finished in the top 5 of the competition. It's the only other open source solution that we could compare it with. So here we can see at the right a graph that shows the normalized cost of each instance over the time, and the black box shows when the solver found the best solution for the specific instance. In this case, we can know that at the 1000 mark we already found the best solution for 7 instances, so this instance will not improve over time. At the 2000 mark we have 15 instances with the best known solution, and only 5 of them will improve over the 2000 mark. So now let's consider disruptions. In this work we only consider invalid time and invalid room disruptions, as the other big disruption is the modifying of enrollments. However, in this dataset, all student conflicts are solved, so a change in enrollment will not cause a significant change in the solution. The solution will continue to be feasible. Here in this graph, we have the time per instance. The instances are organized by university, and we can see in most of them the original solutions takes longer to solve than the disrupted instances. This is explained by the fact we warm start the solver with the original solution. So if we need to do less perturbations to return to normality after a disruption, the instance will be easier to solve. However, if we need to do many perturbations to recover from a disruption, so the warm start solution is wrong or further from the correct answer, the time will increase. We can see the exceptions to these rules are these instances where the execution time takes longer to solve the disrupted instances, and this can be explained by the fact they have more perturbations because the domain is smaller. Here we can see a graph that shows the average room domain of a class and the Hamming distance, and we can see when we have smaller domains we will need to do more perturbations to return to normality, and so we will spend more time. See. So we also compared our model with an integral linear programming model. The main difference of this model is that it uses an integer variable for the starting time of a class. It actually solves the minimal perturbation problem with the same criteria. However, this solution only solves 10 out of 13 instances, but please bear in mind it was created for easier benchmarks. Interestingly enough, most instances exceed the memory limit, and those that don't exceed the memory limit are 1.6 times slower to find a solution than the MaxSAT solver. This can be probably explained by the fact that binary clauses are really optimized for SAT solvers and not so much for integer programming solvers. So the takeaway message is that now more than ever it's important to solve minimal perturbation problems due to COVID, and that complex university timetabling problems can be efficiently solved and encoded in MaxSAT. However, it is really important to have preprocessing techniques to achieve good results in good times. As follow-up, we propose to reduce the search space by solving the problem incrementally. So in each iteration, we increase the domain option of each class. This follow-up work actually was already completed during the delay in the conference, and we now can proudly say that we can solve all instances of the competition within the time limit. However, this can be even improved, further improved with using of MaxSAT cores to increase the domain when needed. In terms of minimal perturbation, we could explore the incremental nature of the problem to avoid repetitions during the search. I hope everything was clear. Thank you. I'm available for questions, and here are the references. Thank you.